Okay, so for this part, we will investigate the RLC in series. And the interesting part about this circuit is I'm going to make the L and C as the load for the circuit to observe the behavior of the voltage drop against these two elements, since they are opposite in angle, right? So they're 180 degrees from each other, technically speaking, in terms of vectorial impedance representation. Okay, so let's go ahead and see how that looks. So let me go ahead and start a new one right here, and let's make it as big as possible. Well, not too big because I need space for the output. Okay, so that's good. All right, so let me go ahead and draw the lines that I'm going to need to connect the components together. So I'm going to need a wire. Typically a rectangle circuit is the way to go for this. So right here, I'm going to be a little more for, and just do this right here. So let's just do this right here. So let me hit escape, get the scissor tool, so edit. We're going to delete this branch right here. We're good. Okay. The reason is I want the L and C to be in series right here. Okay. And the R to be here as a current limiter. And obviously when the impedance of the capacitor and the impedance of the inductor cancel each other out, I end up with a purely resistive circuit. That's what you need to prove if you're doing this in a lab environment. Okay, and there will be a specific frequency where that will happen. And that is called the resonant frequency for a series LC circuit. Okay, well, let's observe it and let's see how that works. So, this time we're going to make sure that not only we'll do a transient analysis, but we're going to look at, over a spectrum of frequencies, the response of the circuit over that whole range. And that's going to give us exactly where the resonant frequency is going to lay. I mean, we could do it with transient, but it will take forever, going down or up the scales of frequencies. Okay? I'll do it either way, so you'll see for yourself what's going to happen. Now, let's go ahead and get our source. And at this stage, we'll start with any value for the frequency for the source. 10 volt is fine. We're going to use the same components we used before for the the RC and RL circuit series. Okay, so for this one, I'm going to do voltage. And right here, I'm going to pick 10 volts. Go advanced. This would be a sine wave. I'll pick 0 volt DC offset, amplitude 10 volts. I will start with 60 hertz to begin with. Again, amplitude 10. No phase shift for the source, 0 degrees. Perfect. Okay, good. I'm going to put my resistor right here. And let's go ahead and add a resistor. Okay, and Command R to rotate. Put the resistor here, give it a value of 10. 10 ohms is good enough for this exercise. Okay, so now we got 10. Ultimately, what's going to happen is we're going to get to a point where, this line here, it's either a short or an open. Okay? So depending at what frequency are we operating at. Okay, so let's go ahead and include an inductor. Good. We're going to put 2 millihenries here. Oops. And we're going to add also a capacitor. Oops, that's not what I want. Okay, that looks good. And put it in here, and this will be 5 microfarads. There you have it. Let's put a ground here. Because your AC analysis is going to require it. It needs a reference. If you're using a probe from a scope, this will be your ground or your reference point. Let's get a wire from the circuit to that terminal. Voila. Now, let's go ahead and get our SPICE directive going so we can actually create a function that has attributes or parameters to control this simulation. And so mainly so I can see what's going on. All right, so especially on the horizontal scale. I'm going to say I want an AC analysis at this stage, still transient, and I want 0.05 or 50 millisecond basically to observe what goes on in here. Okay, perfect. So I'm going to bring this here. Now we're going to run our simulation. Let's make this a little bigger so you can see. And we're going to use our reference voltage, which is right here. Here's our signal. That is the source. That is what we're feeding the system. Now let's look at the output, which is the voltage drop against the inductor and the capacitor. As you can see at this frequency, it's very capacitive. And it's following the voltage there. Good. Let's increase the frequency. So now we can go over here, do the same thing, increase. So let me close this for a second. And go to 6K. Okay, and this one, I'm going to put a couple zeros here. 0, 0. All right, let's run this again. Okay, let's make this big enough. Let's use our reference. Okay, as you can see. Now let's measure this one. Okay, so we're observing a shift to the other side. Okay, so as you can see, doing a transient analysis, it's very painful. It takes forever to figure out, are we more inductive, more capacitive for a circuit overall? What is the behavior? For something like this, you are better off doing what we call an AC analysis or a spectrum analysis, which means inspect this over a range of frequencies. So we're going to change our, so I'm going to delete this here that we have. I'm going to take it out. We're not going to do the trans analysis. And let me just go over here. This time we're going to do an AC analysis. And we're going to tell it how many points. I need about 100 points. It's good. We're going to start frequency. We're going to start at 30 hertz. Okay. And I'm going to go all the way up to 600 kilohertz. Let's see how this works. And that would be our analysis right here. Okay, so let's move this. I can actually move this. Edit, move. Let me see if I can move it with another tool. Drag. There you go. Drag it right here. So this is the frequency range in which I want to play. Okay, well, let's do it. Okay, and now we're going to analyze the output. So, run. Okay, so now what I want you to observe is the frequency range we have here. Okay, based on what we have over there. So it didn't go all the way up to 600K. It just stopped a little shy. Oh, I see. It's using. No, it's linear. All right. So well, let's run it. Let's see what happens here. There you go. So something happened. Do you see this? At a certain frequency, something happened where your circuit was of a certain type of impedance and then it switched to another one. All right. And here it tells you it's either was capacitive and then it became inductive. Well, let's think about this. What's going on here in terms of the equation? Right? What's going on in terms of the equation right here? Right? If you were to write this equation right here, and let's make this a little smaller. Let me just bring it up. Connect my tablet so I can actually write the equation. There you go. And let's say, what is the equation for this one? Oops. Right here. And let me get my pen. Okay, for Z total. Okay, so Z total, which means what is the impedance of this whole circuit? Z total is going to be equal to R, the real components, right? Plus JL omega minus, okay, J over 1 C omega. In other words, Z total is going to be equal to R plus J of L omega minus 1 over C omega. Okay? There is going to be a point where this component is going to be equal to 0, where L omega will be equal to 1 over C omega. That will be a specific frequency where that happens. That will be your resonant frequency. That means it's as equally, inductive as it is capacitive. So if we were to replace this like this, equal 1 over 2 pi f C. And we want to find that specific frequency, F0, when this happens. This happens at a frequency F0, right? So we could say that L 4 pi square F0 square C equals 1, right? So this basically I transported this over here. Okay? So that's fine. So that means F0 square equal 1 over 4 pi square LC, which means F0 will be equal to square root of all of that. 1 over 4 pi square LC. What the heck is that? Is that square root of 1 over square root of 4 pi square LC? And what is that? F0, square root of 1 will be 1. 2 pi, you can extract the 4 pi square root of LC. So at this particular frequency is where you're going to get this behavior right here. As a matter of fact, if we plug our calculator and see if that's true, I can zoom in here, zoom right here, and see what it is. Okay, hang on a second here. Notice I didn't even have to go to 600 kilohertz. Let's just zoom right here. You could see that at this level, we're at about 1.59 kilohertz. 1.59 kilohertz. Well, let's see if that is what we will get with these components. Okay? What is F0? When you're dividing 1 over 2 pi, square root, and what was my LNC here? This is what happens when I do this on the fly, so bear with me. And that's 2 10 to the minus third times C, or what did I do for C? 5 micro, so that's 5 10 to the minus 6. Okay, so F0 is 1 over, let me just do my calculations here. 2 times 3.14, just gross calculations here, 6.28 times 10 to the minus 9. So really it's 10 to the minus 8. So F0 equal 1 over 6.28, 10 to the minus 8. See what that is? 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6, 7, 8 times 6.28 inverted, and that will give me, very nice, F0 is 1.592 kilohertz. That's what I get with my calculator right now. Let's see what the graph said. Right this point right here. Hallelujah. We're right on it. 1.592 kilohertz. So right there, right there. See where my mouse is? It tells me when it, so let me just go do a zoom to fit again, when that happened. Okay, well, now let's try to understand the behavior of this, what we're looking at. Okay, something shift, as you could see. It was going fine, and then boom, it went down, and then back up. That's your total impedance at that point. Okay, because you're measuring voltage right here. So your voltage is associated to your impedance as it switched, but it has switched angle. It has switched basically, what kind is it? Is it more capacitive or inductive? Let's look at the analysis here. As you increase the frequency, as you increase F0, this increases and this decreases. So it becomes more inductive. As you lower the frequency, then this increases and that decreases. So we're definitely capacitive on this side and inductive on this end. This here was just the switch over when that happened right here at this frequency. Okay, so I hope this helped a lot understanding the behavior of an RLC circuit. Now, the next video, we're going to look at R and LC in parallel. Okay, well, let's have fun.